All right, let's jump right into this explainer where we're going to demystify the absolutely critical data science task of building a predictive time series model. If you've ever wondered how modern retailers pull it off, how they manage to optimize their massive supply chains, dial in their staffing schedules, and manage cash flow with such incredible precision, well, the secret sauce is historical data and time series forecasting. So we're going to break down exactly how you can harness Python libraries, specifically stats models and scikit-learn, to actually predict future demand. Here is our roadmap for today. We'll be moving through 6 key steps. 1. The retail forecasting problem. 2. Decoding time series data. 3. Preparing the raw data. 4. Engineering predictive features. 5. Training the regression model. And 6. Evaluating business impact. Starting right off with Section 1, the retail forecasting problem, and anticipating future demand. Let's ground this in reality for a second. Retailers have to predict future demand to optimize their operations, right? Because holding too much inventory means you're wasting money on storage, but having too little means empty shelves and lost revenue. Now, standard machine learning usually assumes data points are independent and identically distributed, what we call IID. But time series analysis is a whole different ballgame. It has to respect the strict sequential flow of time. The data point you collect today is highly, highly dependent on what you observed yesterday. And that temporal dependence introduces some really unique challenges that require specialized techniques to solve. Moving on to Section 2, decoding time series data and really understanding those underlying patterns. So before we can even think about building a predictive model, we've got to understand the math hiding inside our raw historical data. Basically, any sales chart you're looking at is really just a combination of 4 distinct elements stacked on top of each other. First, you've got your trend, which is that overall trajectory, like a brand growing steadily year over year. Then there's seasonality. These are the regular, repeating patterns tied to the calendar. Think about how weekend sales consistently crush weekday sales, or those massive holiday spikes. Third, we have cyclic patterns, which are your longer-term macroeconomic fluctuations that don't follow a strict calendar. And finally, the residual. That's just the unpredictable, random noise left over once you peel away the trend and seasonality. Now, here's a crucial concept, stationarity. A lot of traditional forecasting algorithms absolutely demand stationarity to work properly. What does that mean? Well, if your data set has a strong upward trend, its mean is actively shifting over time, right? That makes it non-stationary. Or if the variance is wildly expanding and contracting, again, non-stationary. If you try to feed that kind of shifting data directly into certain models, they basically fail to find a reliable baseline to predict from. Of course, we don't want to just fly blind here. We use a Python library called stats models to run something called the Augmented Dickey-Fuller, or ADF test. This gives us a mathematical check to see if our baseline is actually shifting underneath us. The null hypothesis here is that the data is non-stationary. So if your resulting p-value comes back greater than 0.05, you fail to reject that null hypothesis. Put simply, your data is non-stationary. You've got a shifting mean or trend that you have to deal with before you start modeling. But hey, if the ADF test fails, we don't panic. We just use a really neat mathematical trick called differencing. It's actually quite simple. You just subtract the previous observation from the current one. So instead of trying to predict absolute sales numbers, you're now predicting the change in sales from yesterday to today. Doing this stabilizes the mean, knocks out the trend, and gets your dataset totally prepped for the heavy statistical lifting. All right, Section 3, preparing the raw data. We're looking at ingestion, cleaning, and aggregation. Every great model starts with pristine data prep. In Pandas, explicitly setting your date column to a datetime object and making it the index is absolutely non-negotiable for time series work. But I really want you to pay close attention to Step 3. You simply cannot drop missing rows in a time series dataset. Let's say you just delete a missing Tuesday. You've literally broken the continuous flow of time. All your historical lag features will instantly misalign. That is why specific techniques like time-based interpolation or forward filling are strictly required. And finally, we'll often aggregate extremely noisy day-to-day data into weekly buckets, which gives our model a much more mathematically stable target to aim for. Next up is Section 4, engineering predictive features. This is all about translating time for the machine. So at this point, we have clean data, but we've hit a massive conceptual hurdle. Standard machine learning models, like a basic linear regression in scikit-learn, are totally blind to the concept of time. They don't know what a Tuesday is, and they definitely don't understand that row 5 happened right after row 4. We desperately need a way to translate those temporal dependencies into independent tabular features that the library can actually digest. The secret weapon here is feature engineering. By creating calendar flags, lags, and rolling windows, we basically teach the machine how to remember the past and anticipate the calendar. We can extract the month or the day of the week and use one-hot encoding so the model grasps categorical seasonality. We'll use autocorrelation plots to figure out our significant lags, and then literally create columns that tell the model exactly what sales were 1 week ago. We also build rolling window features, like a 7-day moving average to capture recent momentum. And for sure, we have to flag major events and holidays to account for those gigantic external spikes in consumer demand. Which brings us to Section 5, Training the Regression Model, looking at the architecture and execution. With our tabular features beautifully engineered, it's pipeline time. But okay, major warning right here. Never, ever use a standard random shuffle on time series data. If you randomly grab data points from 2025 to help train a model that's supposed to predict 2024, your model is illegally peeking into the future. We call that data leakage, and it will 100% invalidate your entire model. You have to use a strict chronological split. You train exclusively on the past, and you evaluate exclusively on the future. Period. Before we unleash a complex algorithm, we always lay down a dumb baseline forecast. A naive baseline just assumes that tomorrow's sales will be exactly the same as today's. Or, if you have strong weekly seasonality, a seasonal naive baseline just predicts tomorrow will match the sales from exactly 1 week ago. We do this to mathematically prove that our fancy linear regression model, loaded up with all those engineered lags and rolling stats, is actually learning something useful. Because look, if your advanced machine learning can't even beat a naive baseline, it's back to the drawing board. Finally, Section 6, Evaluating Business Impact and how we measure success. Ultimately, we have to ask ourselves, does all this heavy data science actually solve the original retail business problem? We evaluate that using specific regression metrics. Mean absolute error, or MAE, is fantastic because it's highly interpretable. It tells the business, on average, exactly how many units the forecast is off by. You can literally walk into a boardroom and say, hey, our forecast is off by an average of 50 units. Root mean squared error, or RMSE, works a bit differently. Because it squares the errors before averaging them, it heavily penalizes big mistakes. We use RMSE to make sure we aren't making massive business-ruining outlier errors, like completely missing a giant holiday demand spike. But a great data scientist doesn't just hand over a spreadsheet full of metrics, right? They provide a really comprehensive visual. By plotting the actual historical sales directly against the model's predictions, and throwing in a stark vertical cutoff line that separates the training data from the test data, stakeholders can clearly see where history ends and our predictive power begins. It perfectly visualizes exactly how well the line of our forecast tracks the reality of actual sales. At the end of the day, your final executive summary has to tether all that statistical math straight back to an actionable business strategy. It's really not enough to just say, well, we achieved an RMSE of 12. You have to explain that the data exhibited an upward trend, that your feature engineering allowed the linear regression model to successfully beat the naive baseline, and, most importantly, what that actually means for supply chain and staffing recommendations. I'll leave you with this thought to chew on as you go build your own forecasts. If your model perfectly predicts the past but fails completely tomorrow, are you forecasting reality or are you just overfitting history? Because in data science, predicting the past is pretty easy, but actually anticipating the future, that is an entirely different challenge. Thanks so much for joining me on this explainer, and happy forecasting.